feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue to look at rational functions. The last time we got together, we looked at key features of irrational functions, and we're going to continue this discussion. So the last feature we looked at was the vertical asymptote, domain restrictions that led to vertical asymptotes and holes. Now we're going to take a look at horizontal asymptotes, and I'm going to go ahead and just straight away give you the rule for finding horizontal asymptotes without graphing or prior to graphing. What we're going to do is we're going to take a look at the function for the rational expression. And what we compare is the degree of the numerator to the degree of the denominator. And so you can see some notation here. N is going to be the degree of the numerator, D the degree of the denominator. If the numerator has a degree greater than the denominator, there will be no horizontal asymptote. If the numerator has a degree less than the denominator, the horizontal asymptote will be 0. And if the numerator has the same degree as the denominator, the horizontal asymptote will be a ratio of A over B, which is the leading coefficient of the numerator over denominator. So let's take a look at some examples. So if in 3a we have the function 3x over x squared plus 1, the degree is, again, the highest powered exponent of the numerator in comparison to the denominator when we take a look at the variables. So the degree of the numerator is 1. It's not listed there, but we can know that the exponent for x is just 1. So the degree here is 1. The degree of the denominator is 2. So in this case, n is less than d. The numerator has a degree that is less than the denominator. Therefore, the horizontal asymptote, which I will abbreviate, is y equals 0. And so we can take a look at this graphically. So we discussed what a vertical asymptote was. A vertical asymptote was a line that a function is going to approach as it goes up. As the graph goes to the right or the left, it's going to go towards infinity or negative infinity. A horizontal asymptote, and I'm going to zoom in a little bit here so you can see it a little better, is a horizontal line that the graph will approach as it goes to the left and to the right. So the line y equals 0, we can see it a little bit here. This graph starts to get closer and closer to that line as we go to the right from above, and as we go to the left, it gets closer from below. Now, what we also see in this position here is that the graph crosses the horizontal asymptote. This can be the case in some instances. In this case, that intersection is an x-intercept. It's not always going to be an x-intercept, but we can algebraically determine if the graph is going to cross the horizontal asymptote or not, and if it does, where that location will be, by setting the equation equal to the horizontal asymptote. So the first part was to find out that the horizontal asymptote is y equals 0. Now, algebraically, if we want to determine that it's going to cross that horizontal asymptote, we're going to set the equation equal to the horizontal asymptote. So we are going to have 3x over x squared plus 2 equal to 0. In this case, I would solve the equation by multiplying both sides by x squared plus 2, and that would give me 3x equals 0. And then I can simplify by dividing by 3, so x equals 0. So the graph will cross, it will cross at an x value of 0 and the y value of 0. So the horizontal asymptote, again, is a line that the function will approach to the left and to the right as it goes towards infinity. And in some cases, it can cross that horizontal asymptote. Here we see the graph crossing at 0, 0. Let's take a look at another example, problem number 3. Problem 3b. In problem 3b, we have x squared minus 4 over x squared minus 1. If I take a look at the degree of the numerator, it is 2, and the degree of the denominator is 2. Therefore, n equals d. The numerator degree equals the denominator degree. So our horizontal asymptote, and again I'm going to abbreviate this as HA, is y equals a over b, a ratio of the leading coefficients. So the leading coefficient of the numerator is 1, and it is also 1 for the denominator, so y equals 1 is my horizontal asymptote. if I want to see if the graph crosses the horizontal asymptote, what I'm going to do is take the equation x squared minus 4 over x squared minus 1 and set it equal to 1. In this case, if I want to eliminate the denominator, I'm going to multiply both sides by x squared minus 1. And so x squared minus 4 equals x squared minus 1. If I were to subtract my x squareds here, I'd get negative 4 equals negative 1, which is an inconsistency. It's a false statement here, and therefore the horizontal asymptote will not be crossed. The graph will not cross the horizontal asymptote. So it doesn't always cross the horizontal asymptote. In some cases it does, in others it does not. So let's take a look at what this graph may look like. I have it preloaded into my calculator. So here we can see this graph actually has vertical asymptotes. The last one did not, but this graph does have vertical asymptotes. We could find those as negative 1 and 1, but what we're looking at here is a horizontal asymptote. That horizontal asymptote would be y equals 1, and so this graph is approaching it. Let me go ahead and graph the line y equals 1. So you can see that it's getting closer and closer and closer to that graph y equals 1 to where we can't distinguish, but if I were to zoom in, we would see a little space between them. So this function has a horizontal asymptote. It does not cross the horizontal asymptote. Now problem 3c, I'll come back to the graph there, but problem 3c, let's go ahead and take a look, is 3x squared minus x minus 6 over x squared plus 6. Again, we have an instance where the numerator and denominator have the same degree. So then the horizontal asymptote for this function is again going to be a ratio of the leading coefficients of the numerator and denominator. So the leading coefficients would be 3 over 1. So 3 over 1 means our horizontal asymptote is going to be 3. Now again, in order to determine if we cross this, and we're determining this algebraically, yes, you could graph this to see if it's going to cross, but algebraically to determine if it's going to cross the horizontal asymptote, we set the equation equal to the horizontal asymptote and look for a solution. So in this case, I would multiply both sides by the denominator. And so what I would get is 3 times x squared plus x minus 6 is equal to 3x squared minus x minus 6. So as I simplify, 3x squared minus x minus 6 equals 3x squared plus 3x minus 18. If I wanted to subtract 3x from both sides, those would eliminate. I could subtract 3x, sorry, if I wanted to subtract 3x squared from both sides, those would eliminate. If I want to subtract 3x from both sides, I get a negative 4x. And then I would add 6 to both sides to get negative 12. Here I could divide by divide by negative 4 to get x equals 3. And so this would cross at the point 3 on the x and the horizontal asymptote 3, 3. So let's go ahead and let's graph this. This last one here. And so here we have, again, this graph would have 2 vertical asymptotes. We could find those algebraically if we wanted to, but more importantly, I'm going to go ahead and graph the line y equals 3, which is the horizontal asymptote. I can see over here to the left of the graph, it is approaching that horizontal asymptote, but not crossing it. I can see over here to the right, the graph comes below the horizontal asymptote. It crosses, and then it comes back up. It gets increasingly closer to that line y equals 3, but this time from the bottom. If I were to go ahead and take a look at the function, let's go ahead and take a look at the table. I could see that at 3, 3, this is equation y equals 4. Yes, so this graph does cross. We're looking at y equals 4 for our equation here. This graph does cross, y equals 3. This graph does cross at 3, 3. You could also see that here. If I want to go take a look at the graph, I could see second trace and go to the value key and type in the x value 3 and see that it does give me the point 3, 3 as part of my curve. So horizontal asymptotes can be approached from the can be approached from the top or the bottom as we move left to right, and can also in some cases be crossed. Now what we didn't look at was an instance of having the numerator having a degree that is greater than the denominator where no horizontal asymptote would exist. This is something that occurs occasionally, but not something that we focus on in Algebra 2. It's more of a pre-calculus topic. So what we're really looking for is there a horizontal asymptote? If yes, then does it cross, and being able to find that algebraically. Now, the last bit that we have to solve for rational functions is the application of rational functions. And in these cases, we're primarily going to rely on the computation methods of the calculator. So let's go ahead and take a look at an example. It says, problem number 4, for a large urban-centered county, the cost to remove chemical waste from a local river is modeled by C of P, which is 180P over 100 minus P, where C of P represents the cost in thousands of dollars to remove P% of the pollutants. Use a graphing utility to sketch a graph for the function. So it does say use a graphing utility, and anytime that we do have to graph this type of information, we are going to go ahead and graph it on the calculator. So what we're going to do here is we're going to clear out everything that's listed so far. And then we're going to create a new function. I did not preload this one, so you can do this with me. This is going to be 180. We're going to label x for p for our calculator's purposes over 100 minus x. Now I'm going to hit the window key, and I'm going to set the x minimum to 0 and the x maximum to 100. The reason I'm choosing 0 and 100 is if we think about the problem, the x value represents percent. The lowest percent you could get is 0. The highest in theory is 100. So let's go ahead and hit zoom and 0. Go down to zoom fit. So technically we couldn't reach probably 100% removal of the solution or percentage of the pollutants, but this gives us the range of possible percentages. Now, what we can see here is that this graph does not actually start at this point. Okay, it looks a little, looks like it might start at this location, but if you think about horizontal asymptotes for this graph, the degree of the numerator is 1, the degree of the denominator is 1, so it actually has a horizontal asymptote at y equals 0. So that's the first thing to keep in mind here as we graph. So part A, we're going to sketch a graph. We want to make sure that we label our graph. So the vertical axis represents cost, and this is in thousands of dollars. The horizontal axis represents percent of pollutants. That's going to be removed. And we can kind of sketch in, I'm going to sketch a line showing that there's a horizontal asymptote at y equals 0. And it does look something like this. So I'll extend my graph a little bit, but we went from 0 to 100 on the x-axis. It says find the cost to remove 25%, 50%, and 75% of the pollutions. Now, here, this is where sometimes we may make a little bit of an error. Generally, when we talk about percent, we start to change it into a decimal, like 0.25 or 0.5, 0.75 for these different percentages. But in this instance, x is already in percent. So what I'm looking for is an x value of 25, 50, and 70. So what I can do is hit second, trace, and go to value because I know the x value. So I can type in the point, type in 25, and it gives me 60. So I'm going to put that point on my graph. I'm going to do the same thing for 50%. So second calc, go to, or second trace, which is the calculate menu, go to value, and type in my value, 50. So this point would be 50, 180. So you can see it is increasing. And second trace, go to value. The last one is 75%. 75% is 540. So I'm labeling these points. I'll move this one a little bit. But I'm going to label these points on my graph as well as labeling the axes because these points are going to relate to the answers. Now, the question said to find the cost to remove 25%, 50%, and 75% of the pollutants. So we want to take our points and put those back into some kind of answer. We could do a quick sentence here. We could also do like a table representation. So remember, cost is in thousands of dollars. So this would be $60,000 to remove. So percent removed would be my second category here, I'm just going to make a quick table. So $16,000 to remove 25%, $180,000 to remove 50%, and $540,000 to remove 75%. So you could put that into a sentence, you could put that into a table. We just want to represent that information in some way that is representative of our graph. Part C says to find the percentage of pollutants that can be removed if $550,000 is allocated to pollution removal. Well, 550,000 would be a Y value. So what I can do here is I can go in and I can input 550, and again, Y is in thousands, so just 550, and graph. And you can see there that it drew a line down there in the bottom. And I want to find this intersection point. So I'm going to do second trace, go down to option number 5, intersect, and make sure I'm on my first curve, somewhere close to where I believe the intersection is going to be at. So it's down here somewhere. We can't see great, but I'm just going to go ahead and hit enter. It jumps over to the second line. I'm going to hit enter, and we don't need to guess. And so what it does is it gives me this point that is going to be very near that last one. And I'll label this point as, we'll round to 2 decimals is fine for now, 7.34 and 550. So 75.34% of pollutants are removed for $550,000. So this time I put my answer in a sentence. Question D says, in mathematical notation, state what happens if the county attempts to remove 100% of the pollution. Well, what we can see here is we can see that as we approach 100, this graph dramatically increases. So the graph dramatically increases. And we might take a look at why does the graph dramatically increase. If I go back to the function, what I realize here is the denominator is 100 minus p, which means that 100 is a restriction on the domain. Actually, 100 is what we call a vertical asymptote. So at x equals 100, we have a vertical asymptote. So the function is going to get closer and closer and closer to 100%, but it's never going to get to 100%. It says state what happens if the country attempts to, or the county, sorry, a typo there. The county attempts to remove 100% of the population. So what we can find is that cost approaches infinity. We could say that cost approaches infinity, or cost increases without bound, or cost will continue to go up the closer that we get to 100%. So we can never remove 100%, and the closer we get to that, the higher the cost goes. Okay, so here we can see an example of how rational functions may be used and how we can use our calculator to solve and to apply those rational functions. This looks like a good place to stop. As always, thank you guys for tuning in, and we'll see you soon.